Hello, my name is Jacob Tarnowski. This summer I worked on a project with Dr. Linder approximating sampling distributions of correlation coefficients under type 1 censoring. Now, for an example of type 1 censoring, imagine an experiment where a bunch of light bulbs are turned on all at the same time and they are left on continuously, leaving them to burn out. Now, under type 1 censoring, a time limit is imposed on the experiment, where once that time limit expires, the experiment ends, and only the data or the light bulbs that have been collected up to that point are observed. The rest are censored. Now, type 1 censoring introduces several problems. The main one being that it leaves the distributions of commonly used statistics, such as correlation coefficients, unknown. Therefore, we are unable to make inference of these statistics. Now, with this information, you would expect that people in industry and people conducting research to avoid using type 1 censoring. However, that is not the case. They continue to use it, but they choose to ignore the impact type 1 censoring has and just report that they had a smaller sample size. Now, we look to build a tool that enables inference to be made of correlation coefficients while also taking into account the impact that type 1 censoring has. Now, the first step of this entire project was to simulate distributions of absolute values of correlation coefficients that have been subjected to type 1 censoring. Now, each one of these distributions we constructed through simulation was built using a different combination of the three parameters: sample size, or n, average censoring percentage, or theta, and a different sample correlation coefficient, or rho. Now, when we look at these distributions we simulated, we found that the shifts in the distributions are predictable given changes in these three parameters. This gave us the idea to use another distribution as an approximation for the sampling distribution. We chose to use the beta distribution. We chose the beta distribution for two reasons. One, it is extremely flexible due to its parameters alpha and beta. Excuse me. The second reason is that it has the same domain as the distribution of absolute values of correlation coefficients. Now, the first step in using the beta distribution as an approximation for the sampling distribution was to find ideal pairs of alpha and beta to construct a beta distribution that best represents the simulated distribution at all 504 different combinations of n, theta, and rho we chose to study. Now, through simulation and using maximum likelihood estimation, we were able to do this quite efficiently while maintaining accuracy and precision. The next step of this project was to move on to modeling our data. Now, using this data that we generated in the previous step, we were tasked with building two models, one to predict alpha and one to predict beta, the two parameters needed to build a beta distribution. Now, in completion of building these models, we'll now have a way to find an ideal alpha-beta pair to build a beta distribution that best represents a sample distribution with any combination of n, theta, and rho. Now, after our modeling phase, we moved on to the phase of our project where we evaluated our model's goodness of fit. We did this in two ways. The first way we evaluated our goodness of fit was with a chi-square test. With our chi-square test, we compared the beta distributions our model generated to newly simulated data to test the overall goodness of fit. Our model performed very poorly under the chi-square test. This is most likely due to an error in my code that I believe is inflating our chi-squared values. Now, we also evaluated our model's goodness of fit using a relative error test. Like the chi-square goodness of fit test, we compared our beta distributions to newly simulated data. But instead of looking at the entire fit of our beta distribution compared to the simulated data, we focused on various percentiles and found relative error at those percentiles to evaluate our goodness of fit. This test, in this test, our model performed much better than the in the chi-square test. However, our results still weren't that good. So for whoever picks up this project in the future, whether it's Dr. Linder, myself, or another student, they're first going to have to build a better model that better represents the data we have simulated. They are then going to have to find a way to generate confidence intervals from the beta distributions our model generates. Thank you.